Hello, this is lecture 5 of mlcourse.ai, and today we're going to cover ensembles. So the basic idea behind that, so why many algorithms are going to work much better than just one. And through bagging, we'll go to random forests. And actually, in practice, this is a very good algorithm, and we're going to cover these ideas behind random forests and why they work much better than decision trees. So if you go to the main course site, mlcourse.ai, so here you can see topic 5, ensembles. So first bagging, then random forest, then feature importance. So pretty much material. We'll go through just some basics. So first of all, bagging. So what's the idea behind multiple classifiers working better than just one? It actually goes back to Condorcet-Jury theorem. It's even 18th century, and I'm going to describe the main idea. So suppose we've got 5 classifiers. I'll just depict them with boxes. So we'll have one classifier, and we somehow estimated its quality. Let's say its cross-validation accuracy is 70%. So for a new test object, we just think that it's going to be 70% correct. But we've got 5 of these, just the same, with the very same accuracy. And what if we just combine votes of these 5 classifiers? So just majority vote. Let's see what happens. So these are going to be classifier 1 and so on, and classifier 5. Suppose votes of all of these classifiers are independent. So just for simplicity, we'll see that this assumption doesn't hold. But if each of these classifiers vote independently, so we can think of 5 just random variables, votes or maybe events that the first classifier is correct. So let's just say that A1 is the random variable, and the corresponding event is that classifier 1 is correct for some test object. And so on till A5. A5, that classifier 5 is correct. Let's just think about the majority vote in case that these events are independent. This actually doesn't hold, but let's just figure out what happens if we assume these events are independent. So these 5 classifiers will form some majority vote. And let's think about these cases when majority vote is correct. So the majority vote is correct actually in 3 cases. So either all of classifiers are correct, or 4 of them, or 3 of them. So majority vote is correct. Let's just estimate the probability of this event, assuming that classifiers are independent. Okay, so we'll have actually 3 cases. So let's just assume that according to cross-validation accuracy, 0.7 will be the probability that each classifier predicts a correct label for some test object. So one case when all 5 classifiers are correct, this probability will be 0.7 to the power of 5. Assuming that classifiers are independent. In this case, of course, the majority vote is going to be correct. Okay, then majority vote will be correct in the second case when 4 classifiers are correct, but 1 is incorrect. So 0.3 for a probability of incorrect classification by some algorithm. But we've got 5 variants, so actually here is a binomial coefficient. 5 choose 1 for 5 variants for some of algo to be incorrect. So there is no dot here, just one. Okay, and the third case is when 3 classifiers are correct. The probabilities will be 0.7 to the power of 3 and 0.3 to the power of 2. And we've got 5 choose 2 variants of 2 classifiers being incorrect. Okay, so if we calculate this, we'll go around 84%. So you see, if classifiers are independent and the accuracy of each classifier is about 70%, then around 84% will be just for their majority vote. Okay, and actually it's surprising. So what if we take 1000 classifiers? So if we do the very same calculations, we'll see that for majority vote, the predicted probability of being correct will be almost 1. And so if we take infinite number of classifiers, then majority vote is going to be absolutely correct. And it's actually strange. So Condorcet jury theorem states that the majority vote is more, I would informally say, more reliable if we have multiple actually juries or classifiers. But the main assumption is that they are independent. So actually the main question is here whether these votes are independent. Okay, and of course in case of machine learning, if we train these classifiers on the very same dataset, of course these votes are not going to be totally independent. But at least this little sketch delivers the idea that the more these classifiers differ, the better will be the majority vote. And this is actually one of ideas behind ensembling, to make these basic algorithms as dissimilar as it possible. Okay, so actually Condorcet jury theorem doesn't hold whatever, so at all. So these classifiers are not independent, but still it delivers some idea that we would like to make them look not similar. Okay, this is actually a very informal explanation, but think of a situation when these classifiers are just the same. So if they totally coincide and their predictions are totally similar, then 5 classifiers are no better than just 1. So in this case, just pick 1. But if classifiers work somehow differently, you can actually mix their predictions, in the simplest case just with a majority vote, and you'll see an increase in quality. So this is one intuition behind ensembling. The other one is delivered with this picture. It's about overfitting. One of Kaggle competition was actually intended to study overfitting. This picture actually shows the idea that in case of ensembling, overfitting might be even not bad. So this is a typical binary classification task. So we separate red dots from blue ones. And suppose the underlying decision function would be some smooth one like this black one. But if we build this green border, we can see that it's totally overfitted. So look, it takes into account all outliers, and you know, we think that this border is not going to generalize really well. But suppose we've got lots and lots of dimensions, and there are very, very many variants actually how to overfit. So we can take into account this particular red ball, or we can skip it. So actually the border can go below it. And actually there are many, many variants to overfit. But if we then aggregate all these, I would say, green decision boundaries, then when aggregated, when averaged, they can produce something like this smooth black decision boundary. So that's actually the idea. So averaging classifier votes is geometrically something similar to averaging these decision boundaries, and actually this averaging can make these decision boundaries better, just smoother and more easily generalizable. Okay, so how can we actually make classifiers different? A very common approach is to use bagging. So bagging stands for bootstrap aggregating. So it relies on a very well-known statistical technique, bootstrap. Bootstrap aggregating. And actually this is the way that we form different datasets, and each classifier will be trained on a different dataset, and that will make classifiers somewhat different. So the idea goes back to, sorry, not this A1 is not here, so just bagging. Okay, so previously we've seen Condorcet-Jury theorem, and we concluded that classifiers need to be somewhat different, and so bagging is actually a technique to do so. Okay, so the underlying technique is bootstrap. It's very famous in statistics. I would only say a couple of words about it. So suppose you've got some very strange distribution, something, let's say 3 model. Like we've got one mode here, one peak, one local maximum here, the second here, and the third here. So let's say we'd like to estimate the median of this distribution. So it sounds really strange. Yeah? We've got a very non-trivial distribution. How can we estimate median of this one? It's much simpler when the distribution sort of resembles some classic one, like normal or Poisson. Then we can actually fit parameters and estimate median with just an analytical formula, or I would say better, mean. The idea of bagging as a non-parametric approach, the idea of bootstrap is to generate subsamples from this available set and estimate median for these subsamples. Okay, so I would draw some dots. So we've got a finite data set, 1, 2, 3, 4, I would say about 10 points. Okay, maybe 11 or 12 points. And the idea of bagging is just to select as a subset, idea of bootstrap. Let's just randomly pick a subset. I'll describe soon how we do it, but let's say that red dots resemble actually depict a subset. So this will be a subset from the initial dataset. And then we just estimate median or any other statistic for this subset. So we calculate medians, and we do it, let's say, 1,000 times. And then we get a new set, median calculated in first experiment. Then we do another subsample, and we calculate median, and so on and so on. And if we do it multiple times, 1,000, we'll create a new vector of medians, and then finally we can just return the mean one, or again a median from this. Okay, just to illustrate, another subsample will be green, so maybe some points are in the first subsample and in the second one. Okay, greens will be just one more subset. So actually this will be the second subset, and red was the first subset. And we do it 1,000 times. Okay, and so returning these medians from medians, we get a really nice non-parametric estimation of the median of this initial distribution. So what we'll actually see, we'll get this red one median for the first subsample, then these, maybe it's here, median for the second subset, and so on and so on. And in the end, we'll come to some, I would say, average of all averages. Okay, so actually Bootstrap is very well known in statistics, and I will tell you about bagging, so how we actually reuse Bootstrap for this idea of making subsets different. So I'll illustrate this picture. So we've got an initial dataset, all these balls of different colors, and we'll take multiple subsamples from this one, calculate different statistics, and then we'll see distributions. So then we'll get a distribution, so it will be called Bootstrap Distribution, and so it actually illustrates this idea of medians. So if this statistics is actually a median, then it corresponds to what I've just depicted. Closer to machine learning, we'll actually have an initial dataset, so our training dataset, and we'll generate subsamples, and we'll train a learning algorithm on every subsample, and we'll have different classifiers. In the end, they will just vote together. The simplest variant is just a majority vote. But let's dig into this idea how we actually take this subsample. Okay, so remember in a previous lecture, there was a very important assumption that our training set is IID. So it's a very famous combination of 3 letters in statistics, in machine learning. So it means that observations are independent and identically distributed. So again, independent. But you see, it's about observations. So that the rows, instances in our dataset are independent and come from the very same distribution, identically distributed. Last time with logistic regression, it helped us to drive some conclusions. So it actually, we used independency there to get log loss from maximal likelihood estimation. So just go for lecture 4, theoretical part. But actually this requirement, this IID, is very important, and it's actually lies behind many algorithms, and actually it's not really very really very non-trivial how you actually take a subsample and also retain this requirement for your observations to be independent and identically distributed. Okay, so how is actually Bootstrap done to get a subsample from an initial dataset? So we'll take a look at a very small example. So we'll have several balls. It is going to be our initial dataset. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so actually we'll take a subsample of the very same length of 10. So we'll have, I will depict here vacant places for instances in our subsample, and the length is going to be 10. The procedure is going to be really simple. So suppose it's just a bag of balls, And okay, so we can draw it more similar to a bag. Okay, not a good drawer. Okay, but the idea is that you put your hand in a bag, you take out some ball. Okay, so you first take out some ball and take a look at its number. Let it be ball number 7. And then you write it down that you've taken out ball number 7, and then you return it back to this bag. Okay, so actually bagging has nothing to do with a bag, but it's easy to illustrate with the idea of a bag and balls, like typically in combinatorics. So bagging stands for bootstrap aggregating, and here we use a bag just for illustration. Okay, and so we return it back, and then we take another one. Let's say the second ball is going to be the 5th one, and again we write down number 5 and return this ball into the bag. And we make this procedure 10 times, and actually the very same ball number 7 can be put out again. Maybe it's here, and there is even some probability that it will be here the 3rd time. Okay, so a subsample will be of the very same length 10, but still instances can occur more than once in this subsample. Okay, let's see why do we need such a procedure. So it's actually for all observations to be independent. So initially we had 10 objects, and each one of them could have been put away with the very same probability of 1/10. So we picked number 7, and the probability of actually picking number 7 was 1/10. So if we throw it away, then we are left with 9 balls, and actually the probability of picking another one is going to be 1/9. You see, so this one was picked with probability 1/10, but the next one, if we threw away ball number 7, then the probability of picking another ball would be 1/9. And so actually probabilities differ, and actually these events, so these balls appearing in our subsample are not going to be independent anymore. So to retain this property of IID observations, we need to return, so actually to put all the balls back, and then the probability of putting out every ball on every iteration is going to be the same. Okay, so and it's actually really simple to calculate the proportion of unique observations in each of these bootstrap samples. So we'll call this bootstrap sample. So it's going to be, the principle is the very same as I've illustrated with calculating medians. So here we had a red sample and a green sample, and here, so these were all bootstrap samples. Okay, and you see the number of, some balls occur multiple times, and the number of unique ball IDs is less than 10, obviously. So I'll proceed with the experiment. Let it be 8, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, and maybe 1 again. And you see we've got balls number 1, 2, 5, 7, 8, and 9 in our sample. So we see balls number 1, 2, 5, 7, 8, and 9 in our sample, but balls number 3, 4, and 6 are actually out of sample, and 10. These are out of our sample. Okay, so first, this procedure of Bootstrap helps us to retain this IID property. The second, it actually helps us to drive various subsamples from our initial training set. And now there will be the third advantage of this technique. We'll see that we'll actually reuse these out-of-sample instances to calculate actually model accuracy. And it will be a very efficient substitute for cross-validation. A bit more math here. So we'll calculate the expected number of balls out of our samples. So let's again have a bag with some balls. Now I'm not going to enumerate these. I'll just say that we've got L balls. So L for length of our dataset. Okay, let's just figure out what's the expected size of unique balls in our dataset. Okay, so if I pick a random ball, I've got 1 over L probability that I actually picked this ball. Let's take a look at some particular ball, maybe this one, and let's calculate the probability that it's not going to occur in our bootstrap sample. So here I'll have again a bootstrap sample. And now I'm interested in a probability that this ball, I will put only one number, this ball 17, that ball 17 is not in our sample. Okay, so I would say P17 will be a probability that ball number 17 is in this bootstrap sample. Okay, and I'm interested in this one. 1 minus P17, it's the probability that ball number 17 is outside of this bootstrap sample. Okay, and so I'm going to figure out this P17 with a dash. Okay, so 1 over L is actually a probability that I've took this ball number 17 or any other when I just put my hand in this bag and took out one ball. So with equal probability I can take any of these. So 1 over L is that I've put out any particular ball. So 1 minus 1 over L is going to be the probability that I haven't taken this ball number 17. But you see, I do this procedure multiple times, and so actually the bootstrap sample will be of the very same length L. So I repeat this experiment L times, and these are all independent. So I need to do this. So the probability of not taking ball number 17. So in order for the ball 17 to be out of this sample, this event should happen L times, and all of these events are independent. So this expression goes to the power of L. Okay, so we've figured out this expression. And now if we've got a really large dataset and L tends to infinity, then we'll get something interesting. So it's actually one of particular limits in calculus. So this limit is going to be 1 over E. Actually, this is the reason why large dataset help to build a nice model. So many assumptions are making in this context that the size of our training set is going to be infinite. Okay, for those who like calculus, we can briefly analyze this expression. So what happens to this 1 minus 1 over, I'll write x, to the power of x? What happens if we if x approaches infinity. Okay, so this expression is the very same as e to the power of x logarithm of 1 minus 1x. Then we've got Taylor expansion for logarithm. So it's going to be e to the power of x, and we can substitute logarithm with actually minus 1 over x. Okay, I'm not going into details. So here you'll see big O of 1 over x. Sorry, small o. Okay, so actually it's about calculus. I'm not commenting it right now, but now you see, so this is actually e to minus 1. Okay, so this expression is e to the minus 1 is approximately equal to 0.37. So now, this is a bit of math about the probability of a ball occurring out of sample. So now closer to practice. So actually we expect about 37% of all objects of all of our instances to be out of sample. Okay, now we've got a real training set. And we took subsamples, Bootstrap subsamples, and we can do it multiple times. And so if we take the first subsample, so there are approximately 33% of initial instances in this dataset. I would say just here, and around 37% of initial instances are out of sample. But you see, each Bootstrap sample is of the very same length L, and we remember that instances can occur multiple times. Okay, and so actually the idea of quickly assessing model quality is called OOB score. And it's so OOB stands for out of bag. So we've got around 63% of our objects in this Bootstrap sample. We can train a model on this 63% of data, and we can quickly analyze this model quality on the remaining 37%. And so for every model, we can calculate each score on exactly these 37% of data. So this is actually going to be much quicker than cross-validation, because while training a big ensemble, so I will call now this an ensemble, so a majority vote or maybe some other combination of all the models trained on these subsamples. But at each step, I can quickly calculate model quality on this out of sample or out of bag data set, and then when averaged, I will get this out of bag score for the model. And it's really very fast, very efficient. It's not perfect, so sometimes cross-validation is preferred, but it can give you an idea of your model quality without actually cross-validation. Okay, so returning to this picture, each of these samples has about, actually sometimes it's rounded to 2/3, so around 2/3 of initial instances are here, and we just assess the quality on the outer 1/3, which is not in this sample. And you see we train all these algorithms, and we can quickly check their quality. Okay, one more intuition, just a couple of words about it. In previous week, in topic 4, we analyzed bias variance decomposition of error. So it can be nicely done for mean squared error for regression. So I'm not going into this right now, just for those interested. It's one more intuition about ensembles, why they actually work better. So the idea of bias and variance is that the error of a model can be decomposed into bias, variance, and some irreducible error. To illustrate it, so if we've got a target, and suppose we're just shooting in this target, and bias would mean that actually our shots are not centered. Okay, so high bias will mean that we are missing actually the desired target. And variance will actually stand for this actually variance. So for this dispersion of our shoots, if they go to the left, to the right, up and down, so this is variance. Okay, so the situation with high bias and low variance is going to be this one. So our shots are actually very well clustered, but they are not in the place they were intended to be. The opposite situation with high variance but low bias is that our shots are not clustered anymore. They've got some variance, but they are around the desired red spot. Okay, then an awful case for a shooter will be this one in the right down picture. Okay, so high variance and high bias, and the ideal case is low variance and low bias. And actually pretty much the same ideas hold for models in machine learning. So those encouraged can analyze this expression, how you decompose mean squared error into bias, variance, and irreducible error. And the very same holds for decision trees and bagging. So if you take a look at the regression problem, here we have some target function f over x. It's a blue one, and our observations are actually distributed around this function with some noise. And this plot shows this bias variance decomposition of the model error for a decision tree. So actually this red curve is going to be errors of our model. So if we just compare the true value and the decision tree prediction and calculate mean squared error, this is going to be this red curve. And this error can be decomposed into this blue one in bias, variance, this green one, and irreducible noise in our dataset. And there are really some nice theoretical reasons for bagging to reduce variance. So actually, again, I'm skipping all this math, but bagging actually reduces variance, and the more estimators you have, the less will be variance in the end. So it doesn't affect bias so much, but this green curve variance is much more decreased, and that's why bagging is going to work better than a single decision tree. Okay, so actually with bagging you subsample rows of your dataset. But if you go further, you can actually subsample features. So remember, we wanted to make our models, our classifiers, to be different, and we can subsample not only rows but also columns. So our features. It's called random subspace method. So if we just select some features, I will just depict like this. For each model, we just select a random subsample of features. And so actually, there is no reason to select some feature twice. So here we'll do just sampling without replacement. Again, the previous one, Bootstrap sample, is often referred to as sampling with replacement. So at each iteration, we replaced our ball in this bag. But here we'll take sampling without replacement. That means if we picked some feature, then we throw it away and then pick a second feature and so on. Okay, so if we combine this with the idea of bagging, we'll subsample rows and columns, and then it leads to random patching. Random patching is actually subsampling rows and columns, so I can actually depict it as taking different patches of the initial matrix. So we've got L instances and D features, and at each iteration we'll just take different submatrices, or we can call them patches. Okay, one patch, they can overlay, no problem. So just taking different submatrices, here we generate different subsets, and then we'll train the very same model on every patch. So actually this is how we get random forest. So random forests are actually random patching with decision trees. So what we currently described, bagging, is a meta algorithm. So going back to this picture, so the idea is really very, very general. So here learning algorithm can be anything, but decision trees turned out to be really very, very cool basic learning algorithm for such a scheme, and this leads to finally random forest. So I'll just abbreviate it as RF. Random forest is actually random patching with decision trees. Okay, and of course there are some peculiarities of random forest exactly, but the idea is just the same, what we covered here. Okay, now closer to random forest. Okay, so if we analyze pseudocode, it's going to be really simple. I know it's not really entertaining to analyze pseudocode, but you'll see it's simple in our case. So we'll have n trees, and on each iteration we'll generate a bootstrap sample. We'll call it xk, and then we'll build a decision tree bk on this subsample. Specifics about random forest come at this point. So for this decision tree bk, for each split in this decision tree, we'll take a look only at some m features, not on all of the features. We'll just analyze a subsample of features. Then we're going to restrict the depth of this decision tree as typically, let's say, we're going to restrict it with n minimal instances, or maybe until a certain depth is reached, so min samples leaf or max depth. And so among these m features, we'll have the best split at every iteration. So for every decision tree and every split, we'll just take m random features. And then the final classifier will be just an average. So we'll average the predictions of all these n decision trees. Then some heuristics, how to set this m. For classification problems, it works nice to just set m almost equal to square root of d. So for instance, if we have 400 features, then 400, then we'll take only 20 features at each time. For regression, a heuristic is to use d over 3 of initial features. And there are some theoretical justifications for in decision trees. Sorry, in a random forest, not to restrict the depth of a decision tree. So going back to this intuition behind random forests, we're not going to restrict max depth. We'll actually overfit basic decision trees, and then when averaged, they're going to build a smooth decision surface like this. Okay, so actually random forest is going to have pretty much the very same parameters as a decision tree. So max depth, mean samples leaf, these are going to be the same. But of course we got now a parameter and estimators the number of decision trees. Okay, some more pictures like this, a decision tree, the bagging and random forest. In a regression problem we can have a look that ensembles work better, and the very same in classification. So actually decision trees don't work really very nice because of variance of their predictions. So the problem is that if we changed our dataset just a bit, maybe throw away a couple of observations or add some more observations, the decision boundary can differ very much. So there is some intuition that a good model shall be stable, that it's not affected just with a couple of samples, and this is actually theoretical justified with the idea of variance of model answers. So actually the decision tree has high variance, and that's why it's not really accurate. But bagging or random forest averages lots of decision trees, and their prediction are now going to be much more stable. Okay, so actually how to work with it in sklearn we'll cover in a practical part. One more feature of ensembles and random forest is feature importance. So going back to this picture of a decision tree, we see that a decision tree finds some features to make some good splits, and actually this can lead to a very nice property of an algorithm to assess feature importance, or how valuable are these features for our task. Okay, so here maybe for this decision tree age is a better feature than income, because a split with the age feature is done previously, so higher in the tree. And actually we can take a look at what features were used by the decision tree to make a split, and we can average this for all trees. So I draw a command on that. So we'll build multiple decision trees. So typically in the random forest you'll use maybe 200 or 300 trees. So we'll have lots of trees, and for each tree and for each attribute we can calculate some statistics of how good is this feature. Okay, so let's say in the first tree here in this split I've got age compared to some threshold, and I can actually calculate the information gain. Remember we choose features and splits based on information gain. So I can just record information gain for age in this decision tree. And I can do it for all splits based on age. So maybe in a final tree there is some other split with age. And I'll just record information gain for this split in the last tree. Okay, again I've got information gain, and so I can actually average this information gains for all values, for all splits on age, and do it for all features. And in this way I can actually create a feature rating. Okay, so speaking about practice, a typical thing to do is just to build a random forest model and then get this feature importance and get some graph like this one. So the model will tell you that it uses some features more, but other features are worse. So actually this is a real research done in Higher School of Economics. Lots of reviews on booking.com and tripadvisor.com were analyzed. They were labeled with average hostel rating. So actually the idea of the research was to analyze different features influencing the hostel rating. So it was actually a content analysis done by researchers, and actually manually people extracted these things like stuff or value for money mentioned in user reviews. And then you see here a regression is built, so the target feature is actually the hostel rating, so the average review rating for a hostel. And this picture shows us that actually mentioning stuff in a review influences the final rating the most. Then people tend to mention value for money, then something else. So actually this investigation was done for customer co-creation, so it's some marketing term, and then they saw that it's in the 5th place, so not so bad. So actually this feature importance is very often used to actually assess how valuable these features are, and it's often used also for feature selection. So if we just see that random forest works really nice, then we'll take a look at this rating done by the very same model by random forest. So the idea is that if a random forest uses different features in our dataset to make a good prediction, let's just use these features. Maybe just we're going to skip these to actually throw away this long tail of not useful features, and maybe for a model to work faster, we'll just keep top N, maybe top 100 of nice features according to this rating. So feature importance is used here and there. And it's also very nice that random forest can give such an assessment. Okay, so actually finalizing pros and cons of decision trees and random forests. So I'll just paraphrase, but let it be here. So the main points are that random forests in practice work much better according to classification metrics. So a typical thing to notice is that a random forest works around 10 or maybe 12% better than a single decision tree. It's very good that random forest is not really very sensitive for hyperparameter setting. So in my experiments, I actually use random forest and logistic regression very heavily, just to get some intuition, to make some conclusions without any hyperparameter tuning. And random forest is such a workhorse, really very popular algorithm, mostly because it can just work out of the box. So without hyperparameter tuning, it can still provide really nice accuracy. Okay, so it inherits the very same pros from decision trees. So random forest can easily work with outliers, with missing data. It doesn't require scaling. So the very same as for decision trees. So with linear models, you should think of outliers, you should scale your features, but here it's not necessary. So that's why it's often used. Random forest is really very easily parallelized. So if you need to train 1,000 trees, you can have 10 machines, and each machine is going to train 100 trees, and then you'll just average the results from all of the machines. Some disadvantages are that random forest is not as interpretable as a decision tree. So we had some pictures depicting decision trees and how this model actually works. So it's really very interpretable. But when you average 500 or 1,000 of decision trees, unfortunately there is no simple way to draw just an average decision tree. So an ensemble typically works very well just because it contains, okay, not just because, but we just covered it, because it averages the result of all these models, 500 or 1,000. And it is much more difficult now to interpret how actually this model works. So typically, the main thing to do is just to build this feature importance estimation, and it's actually the best thing we can extract, the best interpretation that we can do. Some disadvantages or maybe some peculiarities of this model is that decision trees and random forests and gradient boosting based on decision trees, they all don't work that good when you've got lots and lots of features. So when you've got sparse features and millions and billions of features, you'd better go for linear models. And comparing to boosting, so we'll take a look at boosting in detail. So I won't say that it's a disadvantage of random forest. Maybe it's an advantage of boosting, but boosting is typically much faster because it needs much more shallow trees, not that deep. So theoretically, random forest needs deep trees, or even overfitted trees. But gradient boosting builds typically trees of depth from 3 to maybe 7 or 8. So actually it requires much less memory and trains typically faster. But gradient boosting is sensitive to hyperparameters. So typically in a real task, you first start with random forest, and then you tune boosting, and if you tune it well enough, it works pretty much the same as random forest, but faster and requires less memory. Okay, in a nutshell, that was about all these peculiarities of random forests and why ensembles work better than just single models. In the next video, we'll take a look at classification metrics, just to understand these better. And finally, in the practical part, we'll now tackle a real-world dataset and a real business task, and we'll take a look at random forest and logistic regression for this task. But the main goal will be not to compare algorithm, but to discuss this task from the business perspective and to take a look at all these metrics and actually discover which metrics are reasonable to use in this task.